Kids, Charlie Abuso here. We got bonding notes, page 12. This next compound, PCl5, is called phosphorus pentachloride. It's another weirdo compound because it breaks the octet rule. All right? We'll try to draw the Lewis dot diagram. First, phosphorus, of course, has 5 valence electrons. But in order for it to bond with 5 chlorines, we're going to not do it that way. We're going to have to make the phosphorus open up all 5 dots this way. And then the chlorines are going to come in all around. And the chlorine on top will have 7 dots. The chlorine on the 2 o'clock will have 7 dots. At 5 o'clock, we'll have 7 dots. At 7 o'clock, we'll have 7 dots. And at 9:30, we'll have 7 dots. And what happens is the phosphorus with 5 chlorines somehow manages to do this. Now, watch this. Each chlorine is going to borrow an electron. Each chlorine is going to borrow an electron, so they're all going to end up with 8 electrons. But the phosphorus on the inside is going to end up with 10 valence electrons. It's going to break the octet rule because it's too big or too many. Too many electrons. Now, how does this happen? It happens. Phosphorus pentachloride exists. The only way for it to exist is if it breaks the octet rule. It's one of those unusual exceptions, and that's okay. Next, 86. Oxygen and ozone. They're both pure forms of oxygen. Oxygen is O2. Ozone is O3. So we have 2 oxygens or we have 3 oxygens. Ozone is called an allotrope of oxygen. And an allotrope are chemically identical elements bonded differently. And that gives them different properties. O2 is not the same as O3. They're both pure forms of the element oxygen, but because of the way they're bonded, they're not the same. We breathe oxygen to stay alive, and oxygen keeps fires going. If we breathe ozone, it would not allow us to undergo respiration. It would be like breathing nitrogen. It wouldn't work. And ozone will not help fires go. It's got different properties. Ozone does protect us from the harmful rays of the sun, whereas regular O2 oxygen does not. Now, if we try to bond these atoms together, oxygen, I'm going to do it sort of sideways. Oxygen can make a double bond to another oxygen. This is a normal double bond. Both of these atoms now have 8 valence electrons. They make a double bond. They share 2 pairs of electrons. I don't know where to go here. There's nowhere to go. And so what really happens is this third oxygen has its electrons on the outside. So if we were to draw this, this is what it would look like. We have a double bond on the left, and then we have like not really a bond. I'm just going to put in a couple of dots. We have kind of like not really a bond right there. And what happens is this is unstable. This is a stable double bond. This is an unstable single bond. So it immediately changes and becomes this. It immediately changes and says, wait a second, we'll put the double bond over here. That's more stable. But this bond on the left now is not stable. So it immediately goes back. And it goes back and forth and back and forth and back and forth. This bond, okay, these are not stable on either side. So they literally switch back and forth, back and forth. They're trying to they'll hold on over here, and then they'll hold on over here. You can't see my hands. Back and forth, back and forth. This is called a resonating bond. because they seem to go back and forth in a different way. This is another name for this is a hybrid or resonating bond. And there are a couple of molecules that'll do this that don't seem to be able to bond, like SO2 does this also. Now, because it goes back and forth, the double bond is tighter than a single bond. And this other thing over here is not even quite a single bond. So the double bond is tighter than a normal single bond. And this other thing, which is not quite a single bond, is a little longer. And then they go back and forth, back and forth. So they go back and forth so fast to try to maintain their stability. Each bond really is about 1.5 times the size of a normal bond. It's a little bit half and half. It's not quite an exact bond. And the only way to describe it is in this sense of going back and forth, back and forth. Now, ozone exists, and there's no way for it to meet the octet rule process. We have to come up with a different way to name it, and we call that the resonating bond. These bonds, I'll say here, resonate also. They go back and forth. All right, that's the end of this page.